Hello everyone, this is chapter 7.3 where we'll be discussing trigonometric equations and how to solve such equations. First I want to recall a kind of simple trig equation, and then this one's actually kind of a little more complicated, but it's actually just as simple. The only difference, we have to do some actually moving around before we get to the point where it's similar enough to this. But anyways, to this equation now, it says sine of x is equal to 1/2, and we know that sine of what is 1/2? Well, if you think of in the first quadrant, sine of, remember sine is the y value, so sine of pi over 6 will actually give you 1/2. So this is the point radical 3 over 2, comma 1/2 on the unit circle. But more importantly, we just kind of remember at this point, or I guess you could use your sheet and look for sine of what is 1/2. You'll see the reason why I put this in a second. But yeah, we have x is equal to pi over 6. As it turns out, this is not the only solution, because look, sine is also positive in which quadrant? If you remember, all students take calculus, s is in the second quadrant, and in fact, if you look over here, this will also have a y value of 1/2. And this angle here will be 5 pi over 6. So 5 pi over 6 is, well, that is another solution. Now, are these the only two solutions? No, they're not actually the only two solutions. They are the only two solutions in one rotation, but it didn't give us that restriction. If it gave us in the interval 0 to 2 pi, then yes, this would be the only two. But since it does not give us that restriction, we have to kind of list out all of them, and since there's infinitely many of them, there's only so many ways we can do that. But before I actually show you how to do that algebraically, I want to just show you a graphical approach, so I'm going to erase this. Right, so here now I have the graph of y equals sine of x, and I've drawn in black one cycle, and then in red I've drawn one cycle to the right and one cycle to the left, of course. So what I'm going to do now is I'm going to graph the line y is equal to 1/2, because when sine of x is equal to 1/2, that's when those two graphs intersect. So y equals 1/2 is up here, halfway between the x-axis and y equals 1, and this is the line we get here. That's y equals 1/2. Good. And what you notice is that this actually intersects, well, the first cycle here and here, which actually represent the values, x values, pi over 6 and 5 pi over 6, exactly like we saw from the unit circle. But of course there are more. In this second cycle over here to the right, we have these values, and over here we have these values. Now, how exactly we're going to label these is we're actually not going to figure out what they are, but we are instead going to determine how we would find them based on one cycle alone. And what you'll notice is that for pi over 6, if you add 2 pi, you get the value to the right. If you subtract 2 pi, you get the value to the left. And similarly for 5 pi over 6, if you add and subtract 2 pi, you get the other question mark values. So this is also adding 2 pi, and this is also subtracting 2 pi. And this, of course, is because, well, these other cycles are one period away, and the period has length 2 pi. Now, of course, these aren't the only ones. There's infinitely many. So what we're going to do is we're going to write this. Instead of writing pi over 6 and 5 pi over 6, we're going to write pi over 6 plus 2 pi times k, and 5 pi over 6 plus 2 pi times k, where k is an integer. Now, there is actually shorthand for integer. The book doesn't really use it, so if you don't use it, that's fine, but I may use it actually from time to time. And to say something is in the integer, to say something is an integer is to say that it is in the set of all integers. So z, this is a double bold font. This is just the set of all integers. And remember, integers are positive and negative whole numbers, and 0 itself too. So I may use that symbol. And again, the epsilon here just means k is contained in that set. All right. So now moving on to the second example, we're going to solve for x in a similar way, but notice we have sine in two locations. So we're just going to solve for sine first by adding sine to this side. These cancel. So we get 2 times sine of x And I guess we can subtract radical 2 to that side. So equals negative radical 2. That looks good. Divide by 2 now to get sine by itself. So now we get sine is equal to negative radical 2 over 2. Now, we know sine is, well, sine of an angle is radical 2 over 2 when the angle is 45. So that means, well, first off, this is negative. Sine is negative in the third and fourth quadrants. And, well, its reference angle would have to be pi over 4. So this implies that x is equal to what? It implies that x is equal to, well, if you kind of take a look at the unit circle again, so the over 4s in the unit circle in each quadrant are pi over 4 here, 3 pi over 4 here, 5 pi over 4 here, because 4 pi over 4 is just pi, because again that reduces if you remember that trick. And this is now 7 pi over 4. And again, since sine is positive in the first and second quadrants by all students take calculus acronym, then it has to be these two. And it makes sense because they both correspond to a negative y value, and sine is a negative, well, sine is the y value of a point on the unit circle. Good. So, right, so now what? Well, now I'm not going to just write these. I'm going to write these plus 2 pi k each from what we discovered here. By the way, I should have boxed this. So I'm going to write, let's see, it was 5 pi over 4 plus 2 pi k, comma 7 pi over 4 plus 2 pi k. And if you write this, well, for me, I'll just assume that k is a integer. So that I know. So I don't really need to see you including that, but you know, it kind of depends. So maybe if you want to be safe, you can say for k in the set of integers. And if you want to include that in your answer, it's okay. But for me particular, I understand what this means when I just see k. But you know, out in the wild, who knows what people understand. Anyways, oh, by the way, you don't have to use k. That's kind of one of the letters that's most often used for integers. N is another one. So you may see the book use n or k, it just kind of depends. So now we're going to move on to some examples that are a little more extravagant. So let's take a look at those right now. And so now for each of these examples, we're asked to, of course, solve for x like we saw in previous ones. These are a little more complicated. They'll actually involve, well, essentially comparing to quadratics. We kind of saw something like this in 7.2. There was an example we saw where we used a substitution and we called the trig function u so that we can factor it. So we're kind of basically use that here a little bit. For the first one, not so much, so let's just kind of get started. So if you add 1 to both sides first, you get 3 tangent squared of x is equal to positive 1. And then if you divide both sides by 3, you get tangent squared is equal to, well, 1/3. And now if we square root both sides to get tangent by itself, we'll get tangent of x is equal to plus or minus the square root of 1/3. Now if you don't recall, the square root of 1/3 is 1 over radical 3 because you square top and bottom individually. And you can, of course, rationalize this by multiplying top and bottom of radical 3. So you'll actually get radical 3 over 3. And then from here, you can, well, just kind of look at a list or try to recall what tangent values will give you radical 3 over 3. And the angle actually ends up being, well, it's pi over 6. So here, x is equal to pi over 6. But this is kind of funny, look. Since it says plus or minus, what this really tells us is that we don't really care what the sign is, as long as the reference angle is pi over 6. So any over 6 angle in one rotation will actually suffice here, because it'll produce either positive radical 3 over 3 or negative radical 3 over 3 when we take tangent of that angle. All right, sounds a little confusing, but you can think about that a little more if you want, but it has to do with the sign is plus or minus, meaning we don't care what quadrant we're in like we did for the previous two examples. So in this case, I'm just going to write every over 6 angle. Also, from what we saw from the previous two examples, once we found all solutions in one unit circle, one rotation of the unit circle that is, we just add 2 pi k, where k is an integer, to each of those solutions. So here, since there's 4 quadrants that satisfy this, or 4 angles, one in each quadrant that satisfy this, we're going to have 4. So there's going to be pi over 6 plus 2 pi k. There's 5 pi over 6 plus 2 pi k. And the next one will be, I guess, 7 pi over 6 plus 2 pi k, and then finally 11 pi over 6 plus 2 pi k. Now that's how I'm going to write it, and I'm going to be done with it here. But I will say this. Since the period of tangent is pi, and not just 2 pi, you can actually write this a little more compactly. Notice if you add pi to pi over 6, you get 7 pi over 6. Similarly, if you add pi to 5 pi over 6, you get 11 pi over 6. So really, you can ignore the last two, but take away the 2's from here. So write pi over 6 plus pi k, and 5 pi over 6 plus pi k. That's another way you can write this answer possibly, but this is okay too. It's just, well, we're not really thinking about it too much, basically. We're just finding all solutions in one rotation of the unit circle, and then just adding 2 pi k to each of those. So that's what I'm going to do. All right. So now for this one, this is, this one and the next one, of course, involve two trig functions, so what's that all about? Well, they're each a little different, but for the first one, I'm going to notice that they both have cotangent in common, and you may think, well, just divide by cotangent so you don't have to deal with it. And you kind of can do that, but it's a little tricky. You can only divide by a number when it's non-zero. So if we divide by cotangent, that's fine, but we have to consider the fact, what if it was 0, then you couldn't divide by it. So instead of doing that, I'm going to move it to the other side and factor cotangent out. It's basically the same thing, actually, and you'll see that in a second. So cotangent cosine squared minus 2 cotangent equals 0. If we factor cotangent out now, we have cotangent of x times cosine squared minus 2 equals 0. Now by the zero factor property, either this is 0 or this is 0. So kind of like what I was saying earlier, if we did divide by cotangent, you could do that and you'd get cosine squared equals 2, which is what we're going to get here when we set this factor equal to 0. But we also have to consider the fact that, well, if we divide by it, it can't be 0. So in the case where it is 0, you can't divide by it. So what would it be? So with the zero factor property, it's a little easier to see that, so we don't have to think too much about that technicality. So now by the zero factor property, we're going to get cotangent equals 0 or cosine squared of x equals 0. Minus 2 equals 0. But I'll just add 2 to the other side to make it look a little better. All right, so now for this, when is cotangent 0? Well, if you want, you can do this. You can say, well, cotangent is cosine over sine. And a fraction is 0 only when the top is 0, so this implies cosine is 0. And cosine is 0, well, remember, cosine is the x value of points on a unit circle, so that occurs at pi over 2 and 3 pi over 2. So this implies that x is equal to pi over 2 plus 2 pi k, and 3 pi over 2 plus 2 pi k. But actually, if you just write it like this, pi over 2 plus pi k, that actually kind of works, because pi over 2 plus pi is 3 pi over 2. So this adding pi k includes the 3 pi over 2 solutions. Kind of what I said here, only here I didn't write it, but here I am writing it. So this is one set of solutions, but now what about this? Well, funny enough, this actually has no solution, and here's why. If we square root both sides, we get cosine of x is plus or minus the square root of 2. And the square root of 2 is actually bigger than 1. And the problem here, that didn't quite come out on the camera. Let me right there. That's bigger than 1. In fact, if you want to write it out, it's 1.414. And the problem there is that cosine cannot be bigger than 1, so there are actually no solutions to this. And in fact, if you were to graph cosine, just to show you, there's one cycle of cosine, y equals radical 2 over 2 is up here, so there's no intersection. Negative radical 2 over 2 is down below, so there's also no intersection. So here, there's actually no solution. And what that means is that, well, this is the only set of solutions, actually. And you can test them by plugging them into the original equation, but I'm not going to do that. I'll leave that to you. But there you go. And now let me erase this to move on to the next one. So now for this one, similar to the previous one, there are two trig functions involved. But it was different here because we can factor one of them out and then handle each individual equation, basically, and each one only has one trig function. Here we can't quite factor it out. So instead we have to figure out, is there a way we can write one in terms of the other? And there is, because sine squared is related to cosine squared with that Pythagorean identity, sine squared plus cosine squared equals 1. In fact, if you subtract cosine squared, you get sine squared is equal to 1 minus cosine squared. So I'm actually going to do that. I'm going to substitute sine squared with 1 minus cosine squared. And I'll allow you to verify that on your own. And now that we have that, after distributing and combining some things, I'll do it kind of quickly here. Let's see, we get negative 2 cosine squared of x plus 3 cosine of x. And this is minus 3. Distributing this is 2. 2 minus 3 is negative 1 equals 0. All right, and I don't like this negative in front because this reminds me of a quadratic. In fact, if we let cosine be u, this kind of compares to negative 2u squared. Let me write it like this. Negative 2u squared plus 3u minus 1 equals 0, where u is cosine. So this is a substitution kind of problem. Now again, how we would solve this is we would either use quadratic formula or factor, but if you want to factor, I don't like the negative in front. So for that reason, I'm going to multiply through by a negative, so I'll just change their signs really. That, and then factor. So think of it like this. If we were to change their signs by multiplying through by negative 1, how does this factor? That didn't quite come out, but I have written equals 0. I think that looks a little better. Okay, good. Let's see. So the numbers that multiply to 1 are 1 and 1. And to make it negative 3, I think that actually works. They're both minus. Let's see, we get 2u times u is 2u squared. 2u times negative 1 is negative 2u. That's negative u, they combine to negative 3u, and negative 1 times negative 1 is positive 1. Good. No, I'm talking kind of fast, sorry. So we end up getting is that u is equal to 1/2 or 1. Great. Similarly, if you actually apply that same logic here before doing the u substitution, we actually get 2 cosine of x minus 1 times cosine of x minus 1. Meaning using that idea with u instead of cosine will allow us to see easier how we can factor such a thing and then how we can solve from there. So of course, getting from this second line to the third line was me using the zero factor property. And the same thing here, if we use the zero factor property, we get that cosine of x is equal to positive 1/2 or positive 1. And we know exactly when that happens. When is cosine equal to 1/2? Cosine is 1/2 at pi over 3, and cosine is positive in which quadrants? Well, it's positive in the first and the fourth quadrant. So this is going to be pi over 3 plus 2 pi k. You know, I don't have room for it, so I'm going to actually have to erase a few things and write it above. So let me do that over here. All right, so that's a little better with space. So like I was saying, cosine of x is equal to 1/2 when x is equal to pi over 3. So I'll write that plus 2k. Or, well, in the fourth quadrant is where cosine is also positive. So that would be, well, in the fourth quadrant, our over 3 would be 5 pi over 3. So it's 5 pi over 3 plus 2 pi k. And that's it for the 1/2 solution. But now when cosine is 1, well, cosine is 1 actually only at 0. Because remember, cosine is the x value of a point on a unit circle. So that's 1 comma 0, and that's when, well, x is equal to 0. So you can write 0 plus 2 pi k, which is really just 2 pi k. So any multiple of 2 pi works, even when k is 0. So remember, k can be 0, so that works out for us. So I'll just write this, and now we're done with it. Great. We're still not done with 7.3. I still want to show you some more types of equations, for trig equations anyways, that we definitely deserve to see. So let's take a look at those right now. Right, so for this example, we finally see a problem where they give us an interval, so we don't actually have to write 2 pi k. We'll stop at some point eventually. And this one's fun because we can actually do this a different way that I'll show after. But for right now, let's see. They don't both involve the same trig function. It's just cosine and sine. So how can we write them in terms of the same trig function? That's going to be a little hard to do, but remember that how sine and cosine are related to each other are with, well, the identity sine squared plus cosine squared equals 1. So if we get those squares involved, I think we'll be in okay shape, but it's kind of hard to do that right off the bat. Here's what I'm going to do. I'm going to square both sides and see where it goes, because that's what this is screaming to me, to get cosine squared and sine squared involved somehow. So what I'm going to do is I'm going to square this side and this side. Now be careful when you do this, because it's not as simple as just squaring this, squaring that, and squaring that. When we square the left side here, since it's a binomial really, we have to use the binomial squared property. So this is the first one squared plus 2 times their product plus the last one squared. And then this is sine squared. So now we can subtract sine squared to this side, which I kind of want to do, but again, I would rather write it in terms of cosine first, and we know that this is 1 minus cosine squared, as we actually saw previously. So doing that first, I think, will make me feel a little more comfortable. So now if I start adding these two, or I guess adding this and subtracting this to this side, so that we get 0 on the other, well, notice the 1's cancel out. So what we end up getting is adding cosine to cosine is 2 cosine squared plus 2 cosine. This is perfect, actually, because now these two have 2 cosine in common. So if you pull 2 cosine out, what you have left over is 1 cosine for the first term and just the number 1 for the second. So that means using the zero factor property, we get that either 2 cosine is equal to 0, or cosine plus 1 is equal to 0. But we know that's the same as saying cosine is equal to negative 1, so I'll leave it like that. Now, cosine is 0 when x is equal to pi over 2 or 3 pi over 2. And again, I don't need to write plus 2 pi k here, because these are both within one rotation of the unit circle. If I wrote plus 2 pi k, then that would represent values that are not in this interval. Well, the other ones would not be in this interval. So aside from just these two, really, when k is equal to 0. But anyways, here, when is cosine equal to negative 1? Remember, cosine is the x value of points on the unit circle, and the x value of points on the unit circle would be negative 1, only over here, which is 180 degrees rotation, which is just pi. So there we go. These are the solutions, but there is something a little strange in this example. And the thing that's strange is that, well, what we did was something that is not really a one-to-one process. We squared both sides of an equation, and that's not always going to hold. So notice if you have the equation 2 is equal to negative 2, that's of course a false equation, but when you square both sides, what do you get? You get a true equation now. So it's possible that when we plug these in to each side, you get something that isn't necessarily true, but after squaring, well, it would be true now. So notice these three aren't solutions to the original, they're solutions to what we got after we squared both sides. So for that reason, one or maybe all or maybe only some of them are actually extraneous solutions, and we'll only know by checking. So I'm going to check real quick. Sine of x, I'm ignoring the squares here. Sine of pi, when x is equal to pi, so I'm going backwards, I guess. That's 0. This is cosine of pi is negative 1, plus 1 is also 0, so that one's good. Let's see, 3 pi over 2. Sine of 3 pi over 2 is negative 1. Cosine of 3 pi over 2 is 0. Oh, there we go, look at that. 1 is not equal to negative 1, but negative 1 squared and 1 squared are both 1. So in fact, this is our extraneous solution. And pi over 2 actually works. Sine of pi over 2 is positive 1. Cosine of pi over 2 is 0, plus 1 is also positive 1. So in fact, our real only solutions are pi over 2 and pi for this equation. And I mentioned that there is a different way of solving this problem, and it's kind of cool to see. There's actually a graphical way of solving this problem. And basically what you can do is you can graph each side. Now notice cosine, well, cosine has this shape here. This first cycle is this shape anyways. And since we're only in the interval 0 to 2 pi, we only care about the first cycle anyways. Now specifically, since this says cosine plus 1, that means the graph of cosine plus 1 is just the cosine of, well, cosine of x, but then shifted up 1 unit. So it's actually going to be, there's going to be 2, 1, and it's going to look something like this. Where this is 2 pi, this is pi. pi and y equals 1 are the halfway points, pi over 2 and 3 pi over 2. Perfect. And in a different color, let me graph sine of x because that's the other side here. And remember, where an equation has solutions is where their graphs intersect each other. So let's see. Sine of x will look like this. Let me try to do this justice. There we go. And what do you notice? They actually intersect here and here at pi over 2 and pi. And it's pretty easy to see that just by graphing by hand. So graphing is something you always kind of want to carry in your back pocket because, to be quite honest, it makes things a lot more visual and even actually pretty simple to graph, simple to solve, I should say, provided you can graph them. So now I'm going to erase this and move on to the next example. Right, so now what makes this one different is that our argument here isn't just x, it's x over 2. So let's see what that entails. So subtract 3 to the other side, we get 3 tangent of x over 2 is equal to negative 3. Divide both sides by 3, these cancel. So we get tangent of x over 2 is equal to negative 1. Well, if we treat the inside as just an angle, tangent of what angle is negative 1? Well, remember, tangent is negative in, let me just write it here. So we have all students take calculus. So in this quadrant and this quadrant is where tangent is negative. So we're either going to be, let me see. So tangent is 1 at pi over 4. If you kind of remember, a 45-degree angle means your x and y values are the same. So tangent would be opposite over adjacent, so it's something over itself would be 1 in that case. So this is going to be an over 4 and a pi over 4 in those quadrants. There's going to be 3 pi over 4, and that's going to be 7 pi over 4. So this implies that x over 2, the argument, is equal to 3 pi over 4 plus 2 pi k, or 7 pi over 4 plus 2 pi k. Okay, good. Now, this is an x, it's x over 2. And there's a comma here, so there's really two scenarios. But I'm just going to multiply everything by 2 to get x by itself. So let me show that here. You just multiply this whole thing by 2. On the left, you'll just get x. And here we'll get, let's see, that's going to be 6 pi over 4, which is 3 pi over 2. But that's plus 4 pi k now. So you need to be a little careful there. And 7 pi over 4 times 2 is 14 over 4. But 14 pi over 4 reduces to 7 pi over 2 plus 4 pi k. So actually similar to the previous example that involved tangent, since there were 4 of them and it said you can write them as 2 of them even though I didn't do that, I want to show that that's possible here. So notice, if you add 2 pi to 3 pi over 2, 2 pi is 4 pi over 2, and what's 3 pi plus 4 pi? It's 7 pi. So adding 4 pi over 2 to 3 pi over 2, which is really just adding 2 pi, will give you this one here. So these two are really the same as just saying 3 pi over 2 plus 2 pi k. So I know I didn't really justify it too much, I just said it out loud. But what I want you to do is I want you to try on your own to list out a few of these and compare them to these, and you'll notice that they're actually the same list you'll get. And you can check with the original equation, but I'm not going to do that. I'll leave that to you. I'm going to move on to the next few examples, and then we'll be done with 7.3 actually. Alright, so now finally for the last set of examples we'll be seeing in this section, these are really the more complicated ones because we won't get actually exact values that we're used to seeing from the list of things we've developed so far from special angles on the unit circle. So let's take a look. First off, for this first part here, notice they're not both in the same trig function. So since this is secant squared and there is a Pythagorean identity that has to do with secant and tangent, we can write it in terms of tangent squared. In fact, just to remind us what it is, so remember sine squared of x plus cosine squared of x is equal to 1. If you divide through by cosine, that'll make sine over cosine tangent, and it'll also make 1 over cosine secant. So again, this is kind of the best way to just on the fly remind yourselves what those identities are Or of course you could just look at a list of identities if you have that with you. That's fine too. And yeah, we have secant squared in terms of tangent squared. It's just tangent squared plus 1. So this is tangent squared of x plus 1 minus 2 tangent of x, and I'm going to subtract this 4 to this side and write it as a quadratic now. So that's going to be tangent squared of x minus 2 tangent of x, and then these two constants combine to negative 3. This factors as, let's see, so we have tangent of x, tangent of x. The two numbers that multiply to negative 3 and add to negative 2, to write it like this, I guess, multiply to negative 3 and add to negative 2 are 3 and 1, but it has to be negative 3 and positive 1 for that to work out. So it's going to be minus 3 and plus 1. Alright, so now using the zero product property, let me erase this part. Alright, so now using the zero product property, or zero factor property, I guess is what we call it, either tangent is equal to negative 1 or tangent is equal to positive 3. So let me write tangent of x is equal to negative 1 or tangent of x is equal to positive 3. We've actually seen where tangent of x is equal to negative 1 before. Tangent is negative, remember, in the second and third quadrant, well, second and fourth quadrant really. And it's negative, so it's going to be, well, negative 1. Tangent is 1 at pi over 4, so it's going to be a multiple of pi over 4 in the second and fourth quadrant. So it's going to be 3 pi over 4 and 9 pi over 4, 7 pi over 4, sorry. 3 pi over 4 and 7 pi over 4. But notice 7 pi over 4 is really this plus pi, because pi is 4 pi over 4, and adding 4 pi over 4 to this is 7 pi over 4. And more than anything, we can just say plus pi k because the period of tangent is pi. So that's another way of explaining that, and we've kind of touched on that a lot in this section, so that's okay. But now this actually will give you something a little bizarre, because we haven't actually seen this. In fact, this will correspond to an x value that is not a special angle we've seen before. In fact, if you want, you can use inverse functions to say that this is just tangent inverse of 3. Now we can actually do that, but there's a little bit of a problem. And the problem is that, remember that the range of tangent inverse is only negative pi over 2 to pi over 2 exclusive, so the open interval. And tangent is positive, so let me just draw the unit circle so I can see what's going on. Tangent is positive here and here, in the first and in the fourth quadrants. So really what we'll get is we'll get a value in the first quadrant when we use tangent inverse of 3. So if you use your calculator for tangent inverse of 3, you'll get something. But again, because the period of tangent is pi, the other one that it'll correspond to in the fourth quadrant will just be, well, adding pi away from that. So in reality, it'll just be whatever this number is plus 2 pi k. I don't know if it'll come out. I'll just write it like this, plus 2 pi k. So I'll actually write out what this is approximately. So altogether, I'll write x is equal to 3 pi over 4 plus pi k, comma, and now let me approximate this with my calculator, and then after I do that, I'll write plus 2 pi k. So let's take a look and see what that is. I actually got about 1.249 approximately if you round to 3 decimal places. Or if you want to write it just as tangent inverse of 3, you can certainly do that as well. But I'll leave this as our answer now. And this was plus pi k, sorry, not plus 2 pi k. Because of this phenomenon here. Or else we have to include the other one, what you can just get by adding pi to this number here, and then you could approximate that. Anyways, I'm going to erase this now and start the second problem here. Something, by the way, I forgot to include is that we want to consider only solutions for this problem in the interval of 0 to 2 pi. And, well, that's really just because that's what the problem actually says. I just didn't write it. But the reason why they have that for this case is because the number gets so ugly that if you just write 2 plus 2 pi k, it'll just be too long. I guess it doesn't really matter. We can do it anyways. But that's what they ask. So let's just move on and solve. Now, the nice thing here is it's already in the form we like. It looks like a quadratic in the trig function sine. And if you consider u squared minus 3u minus 2 equals 0, we actually can't factor this, unfortunately. If there was a plus 3 minus 2, that still can't be factored. But if it was -3 plus 2, that could be factored. Now in this case, what we're going to do is we're going to actually use a quadratic formula. So here A is 1, B is 3, well -3, and C is -2. So if you recall, quadratic formula says U is equal to -b is +3 now, plus or minus the square root of b squared, that's going to be -3 squared is 9, minus 4 times 1 times -2. Double negative is positive, and 4 times 1 times 2 is 8. So we'll just get this all over 2 times 1. And since 9 plus 8 is 17, we actually just get this, which is nice. Well, kind of nice. If you actually approximate this, I'll do that right now, but I can just tell right away. Radical 17 is a little more than radical 16. Radical 16 is 4, so this is a little bigger than 4. If you add these, you get 3 plus 4 is 7. 7 over 2 is 3.5. So the positive case will result in a value that's bigger than 1, and since u is equal to sine in this substitution here, and sine can't be bigger than 1, then the positive case is ignored. When it's minus, though, you'll have 3 minus something a little bigger than 4, which will be, well, a little bigger than -1, and -1 over 2 is less than, well, its absolute value is less than 1. In other words, it's a little bigger than -1. So we'll be okay there, actually, for the -1. But anyways, that's just me speculating. So now let's approximate and see what values we get. So these are the values I got after plugging this into my calculator for the positive and negative case. So for the positive case, we got 3 point something. For the negative case, we got, where it's minus, the minus case, we got -0.562 after rounding. By the way, these are both rounded to 3 decimal places. And yeah, notice we want to let u equal sine, and sine can't be bigger than 1. So this right away will give an extraneous solution. So it's something to keep in mind. At the same time, well, when sine is equal to -0.562, well, similar to what we did here for tangent, we can look at, well, the inverse of this, but it'll only give us values in the, well, the first and fourth quadrant, because the range of sine inverse is in the, well, first and fourth quadrant. It's in between -π/2 to π/2, but in this case it's inclusive, so they're closed. Right. Now, sine is negative here, so it's actually going to give me a value here. Sine is also negative over here, and it's hard to actually figure what these will be. Basically, we have to do some calculation. They'll have the same reference angle. In fact, you know what? Let me do this. So I'm just going to plug this into my calculator. So I'll get x is equal to sine inverse of -0.562. And this is going to give me the one that corresponds to the angle in the fourth quadrant. And it's going to give me a negative because the range of sine inverse is -π/2 to π/2. So let's take a look at what the calculator gives us here. So I actually got x is equal to about -0.597. Now remember, we're rounding everything to 3 decimal places just because I feel that's approximate enough, unless the instructions told us differently. In fact, these instructions don't even tell us to approximate, so it's even a little more out there. At the same time, you have to make sure your calculator is in radians, or else you may get a different result. Now, remember, this is the negative version of this number here. So as far as an angle in radians goes, that corresponds to the negative rotation in the clockwise fashion. So if you add 2 pi to this, you'll actually get the value that this corresponds to, but in the interval 0 to 2 pi. So I'm going to add 2 pi to this, and let's see what we get. Okay, so using the calculator, I got this value here after adding 2 pi. Now it's hard to understand what this really means, but remember, this is an angle in radians, and recall the one full rotation in radians is 2 pi, and if pi is 3.14, then 2 pi is 6.28. This is a little less than 6.28, so it makes sense that this will be an angle in the fourth quadrant. Now, as far as what the reference angle is, the notation is going to be weird. We could call it x prime or something like that. But let's just think for a second. What is x prime in the fourth quadrant? So remember, in the fourth quadrant, it's just 2 pi minus your angle. So that means x prime is going to be 2 pi minus this. So in fact, in reality, what we end up getting really is just the difference between 2 pi and that, which is really just the number we got previously, but positive now. So actually, x prime is positive 0.597. So the reference angle here, let me show you in a different color. This reference angle, theta prime, is 0.597. Now, why do we care about that? We care about that because since these will correspond to the same y value on the unit circle because it's sine of that, then they actually have the same reference angle. This is in the third quadrant though, and remember that in the third quadrant, we add pi to that value. So adding pi to this reference angle will give us the equivalent angle in the third quadrant that'll give us the sine value of well, this. So let's take a look. So if we add pi to this now, plus pi, let's see what we get. All right, so after rounding and adding pi to this, I got this value, 3.739, and that corresponds to the angle in the third quadrant. That, well, sine of that angle will give you actually negative 0.562. So in actuality, these are both our approximate answers that are within one rotation of the unit circle or in the interval 0 to 2 pi. Now I know this is a really complicated problem, and I said it would be. So you can check this, of course, by plugging this in and seeing that it'll indeed give you these values. And that concludes 7.3, and I'll see you in the next video for 7.4. Thanks for watching.